Welcome to the first part of the advanced level in Nanonetworking and Molecular Communications module. My name is Tuna Tugcu. As we discussed earlier, we inspired from the nature frequently in nanonetworking research. Therefore, in the first part of the advanced module, we will focus on protrusions. The second part of the advanced level discusses the effects of degradation of the messenger molecules on communication via diffusion. So let's start with protrusions. Living cells utilize protrusions to better receive nutrients or information. Protrusions can also be used for other purposes like motility, but our focus will be on the communications perspective. Protrusions are simply projections out of the cell membrane towards the source of nutrients or information so as to improve reception. You can find many types of protrusions in nature. They are found on the surface of the epithelial cells or in the inner ear. You can find protrusions also in the connective tissue cells. A protrusion can be as long as 40 micrometers, and the radius might be several hundreds of nanometers. They can be used to expand the surface area for better reception of the chemical signals from the neighboring cells, for cell motility, healing the wounds, embryonic development, and neuronal growth cone pathfinding. Now let's have a look at the short video at the following link provided by Michael Schell. Note the formation and destruction of the protrusions at the cell membrane. The actin filaments are bundled by the facin proteins and moved by the molecular motors to push the cell membrane out like the poles under a tent. This way the protrusions are formed. So our concern is how protrusions can be utilized to improve the performance of CVD. Remember that classical CVD has limited transmission range and suffers high delay due to the slow diffusion of the messenger molecules. However, protrusions can be utilized to improve the reception process. We call such nanonetworking enabled nodes that are enhanced by protrusions as PNANs. In the analysis, we will model protrusions as cylinders for the sake of simplicity. For a fair comparison in the analysis, we will keep the volumes of the PNAN and the regular NAN equal by subtracting the volume of the protrusions from the backside of the PNAN. The protrusions stick out from random locations on the surface of the receiver faced towards the transmitter. We assume a messenger molecule is received when it touches a protrusion. Now let's have a look at the animations provided by my PhD student Gaye Genç. The first video shows regular CVD when there are no protrusions. The sphere on the left is a transmitter. The sphere to the right is the receiver. At the very right end, you see a circle which represents the face of the receiver that faces towards the transmitter. The messenger molecules are released from this point of the transmitter, and when they hit the receiver, they are shown with red dots. In the circle at the very right end, you see the number of received molecules increasing in time. The second video shows the effect of protrusions. Again, the sphere on the left is a transmitter and the one on the right is a receiver. You can see the cylindrical protrusions on the receiver facing towards the transmitter. Note that the volume of the protrusions has been subtracted from the backside of the receiver. So let's start the video. As the transmitter releases the molecules, they are quickly captured by the receiver. You can see how fast the reception proceeds in the circle at the far right. You may find the details of the implementation in the second paper in the references section. In our simulations, we have dedicated only 5% of the volume for protrusions. For a fair analysis, we have compared the use of many thin protrusions against fewer thick ones. The total volume of the protrusions is the same in both cases. We analyze the effect of utilizing protrusions on the hitting probability. The leftmost graph is a regular case without protrusions, whereas we have protrusions with radius 500 and 1500 nanometers for the other two graphs. The dark blue curve at the bottom of each graph depicts the reception during the current time slot. Then come the second, third, and fourth time slots as you go up. Looking at the results, we can see that using protrusions improves the probability of hit. This is well expected since the protrusions have the effect of moving the receiver's cell's surface closer to the transmitter. We also observe that having many thin protrusions works slightly better compared to fewer thick ones, since it allows an even distribution of the protrusions on the receiver's surface. More important is the fact that earlier reception of the messenger molecules and their removal from the diffusion environment helps reduce the number of residual messenger molecules in the following symbol durations. This results in lower intersymbol interference. Now let's look at what happens to channel capacity. We modulate binary 1 using 50 molecules and binary 0 by not sending anything. In the graphs, the blue curve represents the regular case without protrusions. The green curve is for the thick protrusions, and the red curve is for the thin protrusions. In the leftmost graph, we observe that utilizing protrusions provides a wide plateau for correct decoding. Thus, you have a better chance of picking the optimal threshold and therefore being robust to errors. As the distance between the transmitter and the receiver increases, the benefit of protrusions decreases, but still it's much better than not using protrusions at all. This is a result of the fact that protrusions have the effect of carrying the receiver towards the transmitter. You can find the references for 3 important papers on this topic in this slide. Thanks for attending this lecture. You may now proceed with part 2.